always be deviated from the actual value. So when we started, one of us raised a concern that sometimes the forecast that we are doing, are there no errors? Are there no errors in the forecast that we are coming up with? So basically, we are trying to address them, and we are saying that all forecasts will always be deviated from the actual values. Now, the difference between the forecast and the actual values is what is referred to as the forecast errors. The difference between the forecast and then the actual values is what is referred to as the forecast error. So once you make any forecast, at the end of the day, it will be deviated from actual demand. Either your forecast values will be less than the actual demand, or they'll be more than the actual demand at a point in time. And once that happens, we say there are errors in it. Now, these are the various ways of looking at it. We have what we call the mean absolute deviation, which we call the MAD, M-A-D. The next one is the mean absolute percentage deviation, mean absolute percentage deviation, MAPD. The next one is the mean square error, mean square error, mean square error, MSE. The next one is the root mean square error, RMSE, root mean square error, RMSE. So these are the various ways of measuring forecast errors, or the errors in any forecast. We use these various methods to measure them. Now let's look at the first one, the mean absolute deviation. We said it is the absolute difference between the forecast and the actual values. What we mean by absolute difference, sometimes you calculate the difference and you realize that it is negative, depending on whether actual demand was more than the forecasted or the forecasted demand was more than the actual. Once you have negative values in the differences, we are saying pick the absolute values. That is what we refer to as the absolute difference. So if it's negative, you pick the positive of it. Now the AMD is given as 1 divided by n summation the modulus sign dt minus ft. These signs we call them the modulus. That is what takes the absolute value of any negative value. So the t is the period number. The dt is the demand in that period. The dt is the demand in that period. The ft is the forecast for that period. The ft is the forecast. The ft is the forecast. The n is the total number of forecasted periods. The n is the total number of forecasted periods. The n is the total number of. So please put down this formula. AMD, mean absolute deviation. Mean absolute deviation. Mean absolute deviation. So that is one way of calculating the errors. Now let's go back to our data. You realize that when we're using our alpha to be 30%, our forecasted values there were 37, 37, 37.90, 38.83, 38.28, 40.29, 43.20. These were the forecasts, and then these were the demands. So our error is the difference between the demand and the forecast. So 37 minus 37 is 0, but here we don't write 0, we just put dash. Now the next error is 40 minus 37, that gives us 3. The next one, 41 minus 37.9, that gives us 3.10. The next one, 37 minus 38.83, that gives us negative 1.83. But remember, we said we were looking at the mean absolute deviation. So the mean absolute deviation here is the modulus or the absolute values. So basically, anywhere you see negative, you pick the absolute value of it. That is what we refer to as the mean absolute. So we pick the absolute values of all of them and then sum them. Once you sum them, you realize that it is 53.41. If you had not picked the absolute values and then you sum them, you would have had 49.31. And once you did that, you would have had your mean absolute deviation to be wrong. So we now know that our sum of the dt minus ft is 53.43. But remember, the formula was saying that it is 1 divided by n. So once you go back, you realize that your n here, number of periods. So calculate, count them and see how many they are. Don't go and start to count from the periods 1, 2, 3, 4. No, count from where the values were. You realize that there were 11 values. 11 values. 11 values. Don't make the mistake of going to write 12. It's 11. We added 11 values here to get the 53.41. So it's 53.41 all divided by 11. And we have our mean absolute deviation value to be 4.85. 4.85. Now you realize that when viewed alone, the mean absolute deviation, we are saying, is very difficult to access. So what do? We have to use the other ways as well. Now let's look at the next one. The next one is the mean absolute percentage deviation. Mean absolute percentage deviation. Mean absolute percentage deviation. We said it measures the absolute error as a percentage of demand rather than per period. So remember, in the other one, we're measuring the absolute value, the errors in relation to the time periods. The errors in relation to the time periods. But however, if you are looking at the mean absolute percentage deviation, what we are doing is that we are measuring the absolute errors as a percentage of demand. So it's not divided by n. It's not divided by n, not divided by the time period, but it is rather divided by the demand. So percentage of the demand. So let's go back to our data. You realize that our absolute value was still 53.41 for the summation of the errors. Then you realize that the summation of our demand, when you add all your demand, is 520. When we add the demand, it's 520. So that is what is here. So you realize that it is 53.41 all divided by 520. That gives us 0.103. 0.103. 0.103 or 10.3%. 0.103 or 10.3%. So that is the mean absolute percentage deviation. Now the next one is the mean squared error. Mean squared error. Mean squared error. Mean squared error. Now with the mean squared error, each individual error is squared, and then these values are summed and then averaged. So what it means by the mean square error is that we sum or we square all the errors, each individual error for each of the time periods. We square them and then we divide by the time period. We square them and then divide by the time period. So in the mean squared error, you realize that we would have squared our 3 here to get 9, squared our 3.1 here to get 9.61, squared our 1.83 to get 3.35, squared our 6.72 to get 45.15. Now, once you are done squaring, you sum all of them up. You sum all of them up, and that gives us 376.04. 376.04. So 376.04 divided by the number of periods is 11 periods because there were 11 numbers summed. And that gives us 34.18. 34.18. 34.18. Now we've already looked at linear regression, the demands. We've already looked at this. We said in a linear regression, it relates to demand. So the demand is the dependent variable to an independent variable, where we said y is equal to a plus bx. And we said to find a is equal to y bar minus bx bar, just like we're doing for the linear trend lines. The linear trend lines, they were basically the regressions that we were trying to calculate. So you need to take notice of this formula. Take notice of this formula. That is what we've solved 2 examples on this already. So there's an example here. Any question on what we've done so far?